Hi, everyone. I think we're ready to make a start. Welcome to the second day of SBC. Today, our first session is going to be on payment channels. Before anything else, I'll make a quick safety reminder for everyone to please keep the aisles clear. It's a fire safety risk, so there's enough chairs today, but if the chairs spill over at any point, just make sure that you go into the spill-out area and not into the aisles. Giving our first talk will be Atai Tasari. Welcome, Atai.
Thank you. Am I on? Cool. So hi, my name is Itai, and nice to meet you. I've just finished my PhD at the Technion, and today I work at Starkware. I'll present our paper titled Mad HTLC, because HTLC is crazy cheap to attack. So HTLC is a smart contract used as a building block in many cryptocurrency systems, example, Lightning Network and payment channels. And sadly, it's known to be vulnerable to bribery attacks. In this work, we show these attacks include many more systems than previously thought, and that they are actually way cheaper than we previously knew. We also present a fixed, modified HTLC contract named Mad HTLC, which is secure and incentive compatible. I'll start with some background. Oh, sorry, this is a joint work with Matan, Alex, and Itai. So we have blockchains, right? The point is to have transactions of internal tokens among the system users, and we use the blockchain as the main data structure. The system is operated by miners. They put transactions in blocks and receive transactions fees for doing so. And miners trivially want to optimize the fees they receive, and we call these optimizations or optimization opportunities MEV, miner extractable value. The system tokens are associated with contracts, smart contracts. These are simple predicates that are evaluated on transaction data, and if the predicate is evaluated to be true, then the transaction can transfer the tokens associated with the contract. So in this example, we have an input contract, we have a transaction that provides some data, the predicate is evaluated, and then there's a new output contract, and some fees are allocated to the miner. Let me just say this is a UTXO model slide, but similar things can be said about Ethereum, which is account-based. But for all intents and purposes, this is the same. I'll use the term redeem a contract when referring to a contract that is being depleted, when all of its associated tokens are transferred to a new contract. Moving on to the HTLC contract, which stands for Hash Time Block Contract. It's a simple contract established by two users, two parties, Ant-Man and Batman for these slides. The parameters include a hash digest of a secure cryptographic hash function, and a timeout T, which is measured in blocks. And as I mentioned, this is the main building block for many cryptocurrency systems, example, the Lightning Network. So how does the contract work? What does the predicate say? So two options. First option, Ant-Man can get the tokens by providing a suitable pre-image for the hash digest. So we call this the hash lock. Alternatively, Batman can get the token after the timeout elapses. Okay, so we mentioned the timeout, T. Simply wait, and you can get the tokens. Observing the blockchain, let's say we initialized the HTLC on block X. This means that by providing the suitable pre-image, Ant-Man can get the tokens starting at block X, or Batman can get the tokens at block X plus T and onwards. And obviously, only one of them can get the tokens, right? Because removing the tokens redeems the contract. And also know that the miners are those who pick which transaction is included in the blockchain, and therefore the miners choose which of these parties get to redeem the tokens. When systems use HTLC, they make an implicit assumption that says that if Ant-Man publishes the redeeming transaction with the pre-image before the timeout, then that transaction is indeed included in the blockchain by the miners. Okay, this is used in all the systems that I'm aware of that use HTLC. And supposedly, the timeout is long enough for that to happen. But there's no issue here. This assumption neglects the miners' incentives. The miners are those who pick which transaction is included, and this doesn't address this at all. So consider the following example. Batman can bribe the miners to exclude Ant-Man's redeeming transaction until the timeout elapses, and then to include his transaction instead. Example, say Ant-Man paid 1 token as fees for his transaction with a pre-image, and the HLC holds 5 tokens. So in this example, Ant-Man would have gotten 4 tokens, 5 minus 1. Batman would have gotten none, and the miners would have gotten 1 token. Instead, what Batman can do is offer some bribe, say 2 tokens for the miners, which would result with Ant-Man getting nothing, Batman getting 3 tokens, and the miners getting 2 tokens. So clearly, this is better for the miners, who are those who choose what happens. Okay? So there is an opportunity for a bribe here. Previous work by Windsor et al. Discussed this attack, and they proposed to implement this or to facilitate these bribe opportunities using smart contracts. Specifically, their contracts were rather elaborate, meaning they could be only operated on Ethereum, because Bitcoin has a rather limited contract language, which does not facilitate this type of bribery attacks. So they only operated on Ethereum. And another downside of that was that the contracts required prior deployment. That means there was a setup phase for this attack, meaning there were costs regardless if the attack succeeded or not. They have a rather elaborate analysis with two main results. There are 2 options for how much the attack would cost. There is the least expensive option. I'm not going to get into much details about this, but the cheaper option is independent in the timeout, but the expensive option is exponential in the timeout. And this suggests that you can increase the timeout and make the attack too expensive. OK, so in this work, we show this is actually rather cheap to attack the HLC. And also, we can attack on Bitcoin. Our attack version, named 2.0, simply uses the transaction fee mechanism. Okay? No smart contracts, just use the fees to bribe the miners. This makes it Bitcoin compatible, and it requires no prior deployment, meaning there are no costs. You only pay if the attack succeeds. You don't have to set up the attack and pay for that. We analyze this as a game played by Ant-Man, Batman, and the miners, and consider rounds or sub-games corresponding to the creation of the T blocks of the timeout. We use the sub-game perfect equilibrium solution concept, which captures the ongoing decision-making that players make. At each block, both Ant-Man and Batman have to decide what fee they offer or re-offer for their transaction, and the miners have to choose if to include which transaction to include. A quick intuition for sub-game perfect equilibrium analysis is the game of tic-tac-toe. What you would do when you play tic-tac-toe, you would simulate all the possible extensions in your head, and you say, OK, so if I take this move, then will result in this sub-game, an extension of the game, and so on and so forth, playing for both sides, essentially. And you'd end up with all the possible outcomes, and you would propagate back the outcomes you wanted to get to, a process which is called backward induction. So this is what we do for the analysis of the HCLC attack. The results. The required bribe is independent in the timeout. This means this is a conceptual problem, and simply increasing the timeout does not help. We also analyzed the actual cost and found instances on Bitcoin network, on the main network, where a $2 bribe could have resulted with a $26,000 reward. So the attack is really, really cheap and really profitable. I'll say that we haven't exhibited actual instances of the attack, just the attack opportunities. So we say HLC is crazy cheap to attack. There was a suggestion that maybe we can use counter-bribe. Maybe Ant-Man realizes that Batman is bribing the miners to get his transaction included, and maybe Ant-Man could counter-bribe or increase his fee. So this would result in some bidding war, in a sense. And we analyzed this as well. And we showed that obviously there is some sort of asymmetry here, because Batman is bribing for the future and Ant-Man is paying for now. So there is some sort of asymmetry, and Ant-Man can win by offering 1% of the secured amount. So we had 5 tokens locked in the contract. That would be 1% of that. Comparing to Bitcoin fees at the time, this would mean 4 orders of magnitude overhead compared to the fees he was supposed to offer without the attack. Okay, so this is very expensive in terms of fees to protect the HTLC using this method. Okay, so now after everything is lost and HTLCs are broken, there's an alternative. Let's see. We call this mad HTLC. The point was that the vulnerability of HTLCs was from the fact we neglected the miners. We just didn't care about their incentives. So let's not do that. Let's consider them as first-class participants in the contract. Let's incentivize them to enforce the desired execution and to deter attacks. Okay, this is, for me, the most important slide in this talk. We want to use the miners to enforce the correct execution. Quick overview about Mad HTLC. It's a plugin replacement for HTLC. I'll show you its design. It's a universal composability security proof, and it's an incentive compatibility proof. I'll show its implementation for Bitcoin and Ethereum and main network deployments. And I'll present our Bitcoin MEV infrastructure. OK, so MAD HTLC. MAD standing for Mutual Assured Destruction. This is an idea from game theory, most commonly used to describe the Cold War. The US wouldn't nuke the Soviet Union because they would retaliate with nukes, and both would lose. Okay, so this is a deterrence mechanism, and which simply meaning if I attack the other party, they will attack back, and we both end up losing. So let's not attack. The way we implement this for Mad HTLC is if Ant-Man or Batman misbehave, then they both end up losing. Mad HTLC comprises 2 subcontracts. The first, named the deposit contract. This is the main HTLC functionality. The second is the collateral contract, which is optional and auxiliary, which I'll discuss in a bit. They're separated for Bitcoin compatibility, but on Ethereum, they can be consolidated. Their parameters are really similar to an HTLC. So we, instead of having 1 hash lock and 1 time lock, we now have 2 hash locks and 1 time lock. Okay, so we added 1 hash lock. The time lock is just as the HTLC time lock. Hash lock 1, which is the first hash lock, is just like the HTLC time lock, the hash lock, excuse me. And the hash lock 2 is a new hash lock we added for this design. OK, so how does the contract look? This is the deposit one, the main functionality. So we have the first option, which is Ant-Man getting the tokens by solving the first hash lock, which is just like in the original HTLC. We have the second option, which is Batman getting the tokens with the time lock, which is really like HTLC. But now there is an additional constraint. He also has to solve the second hash lock. Okay, so now Batman has to provide a preimage for the second hash lock to redeem the tokens. And there is a third option, which is completely new compared to the original HTLC, where anyone can get the tokens by providing the 2 preimages. Intuitively, if both Ant-Man and Batman try to redeem the tokens, then they reveal both preimages, and then anyone can use the third option to get the tokens themselves. And when I say anyone, I actually mean any miner, because the miners are those who choose which transaction is included in the blockchain. So let's say I'm a miner and I see a transaction that uses both preimages to try to redeem tokens. I can simply replace the destination address with my address and get the tokens myself. Okay, so I'll refer to miners as those that get the tokens, but anyone can actually do that. Essentially, the third option creates an MEV opportunity for miners. OK, the collateral contract, the optional auxiliary one, quite simple. either Batman gets the tokens after the timeout, or any miner, say anyone, but any miner can get the tokens after the timeout with the two pre-images. The parameters are the same as the deposit contract. OK, so why does it work? The game plan for this proof is as follows. First, we're going to use, or we're going to describe the possible interactions any party can have with this contract using the universal composability framework. By interactions, I mean the creation, the initiation, and the redeeming of the contract. We just list all the possible interactions and then prove these are indeed the only possible interactions using this framework. For example, miners initially do not have both pre-images, okay, as an example for a constraint. OK, so once we do that, we present the protocol of how to actually interact with the contract, protocol pi. We describe an ideal functionality that states the possible interactions as we want them to be. And we prove these are indistinguishable. OK, so this is a classic UC proof in a sense. Obviously, this took quite a while, more than I spent on talking about this. But this is like a go-to UC proof. OK, so once we prove the possible interactions with the contract, we can describe the resultant game of these possible interactions. OK, so now we describe the possible moves, and we can describe what player can and should do in order to maximize their revenue. So again, a game played by Ant-Man, Batman, and the miners. Again, using the SPE solution concept. Again, we have T rounds where each action results in a subgame of the remaining rounds. And we show this is indeed incentive compatible, meaning no party gains by deviating. Or in other words, you don't have an incentive to attack. Quick intuition about this. If at most one of Ant-Man or Batman reveal a pre-image, then the miners can't redeem the contract themselves, okay? Because only one of the pre-images is revealed. The third option is not available, resulting in either Ant-Man or Batman getting the tokens as intended in the correct execution of an HCLC. Okay, this is described here in the red squares. However, if both Ant-Man and Batman try to redeem the contract, meaning they both reveal their respective pre-images, enabling the third option, and then the miners can get the token themselves. Okay, over here. And this illustration also shows why we need the auxiliary contract. And the point is to break the tie for Batman in case Ant-Man publishes the pre-images. Okay, so if Ant-Man publishes the pre-image, then Batman knows he lost the tokens, right? If he doesn't do anything, the tokens go to Ant-Man. If he publishes his pre-image, then the tokens go to the miner. So we want to persuade him or to incentivize him to not publish his pre-image. And this is why we use the collateral contract. Okay, so we essentially reward him by not publishing the pre-image. This is here on the right-hand side. All right. So it is secure. It is incentive compatible. Can we implement it? The answer is yes. So we implemented it both for Bitcoin and Ethereum. The overhead compared to the original simple HTLC implementation is quite cheap in my expense. In Bitcoin, that would have been $5 for a larger contract in fees. For Ethereum, we have two implementations. One is the basic simple one, slightly more expensive. But we also have an amortized version, which costs about the same order of magnitude. All right. Point is, the overhead is independent in the secured amount. Okay, we compare this to the counter-bribing option, which resulted in a cost which is a linear in the secured amount. This is independent. So theoretically, you can secure how much money you want without having an additional cost. And specifically, for example, this is way cheaper, like 50 times cheaper. And I should also mention that for payment channels, the HTLCs are usually deployed only if there is some sort of a foul play or a unilateral closure of a channel. So the overhead here is paid only if there is some mishap happening. So not always. All right. So let's deploy these contracts on the networks, both Bitcoin and Ethereum. So we deployed the contract on Ethereum, and actually some of our transactions were front-run. Okay, so our tokens were stolen by some MEV bots, and this is 1.5 years ago, so this was more surprising than it is now. But yeah, so somebody took our tokens. They saw our transaction with 2 pre-images, created a transaction of their own, and took the money themselves. I was happy that someone stole my money. OK, so yeah, success. This means this is a viable solution. Ethereum enforces this correct execution. On Bitcoin, that didn't happen. Nobody stole our money, which made me sad, in a sense. And the question is why? Why wouldn't anyone take our money? And we asked ourselves, is it too difficult? And we realized, hey, no, we can do this. We can implement this Bitcoin MEV software mechanism by patching the standard Bitcoin client named the Bitcoin Core to support this MEV opportunity. So we have 2 patches. The first is to support the specific HTLC bribe accepting mechanism, which means the patch or the patch code looks for these future bribing transactions and realizes that it should exclude Ant-Man's transaction until the time it elapses. This required about 150 lines of code. We also have a general purpose MEV infrastructure that actually exports all of the transaction data to an outer Python model where you can implement whatever logic you want. Example, enforcing the mad HTLC contract, say detecting 2 pre-images, creating a transaction of your own, etc. Okay, so this required 350 lines of code. For me, that's relatively low effort. Okay, so this means this is doable and feasible. All right. To conclude, HTLC is vulnerable. The attack applies to Bitcoin as well, not just Ethereum. The attack is cheap and profitable and doesn't require a prior deployment. It relies on MEV. It's easily implementable. The problem is conceptual. It's not some parameter issues. We present mad HTLC, a secured solution. It's a simple plugin. You can just use it instead. Minor overhead, secure, incentive compatible, easily supported by miners, and the source is available. Thank you.
Thank you, Itai. Any questions?
Hi, thanks for the talk, really nice one. In the first part of the talk, when you presented the attack against HTLC, it seems to me that the fact that there is a hash lock is independent, or in other words, it seems that the attack is also possible for any time lock contract. Is that correct?
Yes.
Okay.
Yes, but the solution is designated for the hash lock problem, but essentially any time-dependent contract is susceptible to these censorship attack in a sense.
So it wasn't, just to confirm, compared to the original HTLC, is there more funds locked in the 2 contracts compared to the original one, or is it the same amount?
It's an additional epsilon just above the expected transaction fee in a sense for the collateral. So if you don't want the collateral, then you can just, or let me rephrase. The solution requires Batman to deposit some sort of a collateral as well. The collateral contract requires an additional epsilon transaction fees tokens to sway into the correct bit.
So this would make sense for like large HTLC transactions. For very small ones,
Yes.
it would be more locked.
Yes.
Yeah. Perfect. Excellent. Really cool work.
Thank you.
I guess a follow-up from my question before. So for when a solution for the time lock contracts only?
Sorry?
So you match STLC, the solution that you presented is heavily relies on the fact that it's an STLC contract.
Yes.
So when are you working on a solution for TLC only, for time lock contracts?
Yes, and maybe next year okay, so self-promoting, we have another paper called Ledger Hedger, which addresses this issue, but maybe I'll present it next year. Should it be accepted?
Next Auckland paper then. Thanks.
Thank you.
You also mentioned that the amount of time that the hash lock contract is running for does not impact the cost of the bribery attack. Why is that?
Because, let me answer this precisely. When you consider the backward induction nature of the analysis, you get either one of three options. Either no relevant transaction is accepted, or the Ant-Man's transaction is accepted and T-1 transactions, or Batman's transaction and T-1 transactions, other transactions. Okay, so essentially when you compare option 2 and option 3, you still get T-1 unrelated transactions included. So it doesn't matter what T is. And the difference is only between Batman's bribe and Ant-Man's fee, essentially.
Okay.
Okay.
Real quick, I may have missed it, but could you say a little more about why you're not seeing these attacks on Bitcoin? Is it just no one does MEV yet, or is there a more fundamental reason?
I can only speculate. I think that in order for a bribe to happen, someone has to offer the bribe and someone has to be willing to accept the bribe or to look out for the bribe. I'm not sure that there are efforts in this direction currently in the Bitcoin mining community. Perhaps because most of the reward is from the newly minted tokens and not from transaction fees. But I suspect / fear that once the block reward diminishes, then fees would become more important, and then we would see this happening more often. And also, Ethereum is much richer in its contract language. You have way more convoluted and complex contracts which you can attack. Bitcoin is rather simple. So,
Any more questions? If not, then let's thank our speaker again. Very nice job.
thank you.
Can we now welcome Luca Samari to give the next talk, which is on generalized channels from limited blockchain scripts and adapter signatures.
All right, thanks. So I'm Lukas Aumer. I'm a PhD student at the Technical University of Vienna. And I want to talk a bit about the generalized channels from limited blockchain scripts and adapter signatures. This is actually a joint work together with Ozan Ersoy, Andreas Erwig, Sebastian Faust, Christina Hostakova, Matteo Maffei, Pedro Moreno Sanchez, and Siavash Riahi. So actually we present an efficient, application-agnostic, cheap, and interoperable off-chain channel solution for cryptocurrencies. And I'm going to elaborate a bit later more on what exactly this means. I want to quickly point out that this paper appeared in last year's Asia Crypt. Okay, so what is actually the problem? Why do we care about this? So we have this in permissionless permissionless cryptocurrencies. We usually have this global data structure called the blockchain. And globally, this records basically every transaction. And on top of this, we have a global consensus that basically needs every user to verify every transaction. And this creates kind of a bottleneck, which is usually results in a fixed block size and some average block time. And obviously, this leads to a limited throughput of transactions and potentially also to high transaction fees. So there are many different ideas on how to address this issue. One of them is off-chain protocols, where basically the idea is that let's not put every transaction on the chain, but instead we kind of exchange the transaction off-chain, and we use the blockchain more or less only as a fallback in case that something goes wrong. And specifically in this talk, I want to focus on payment channels. And what are payment channels? Let me quickly give you an introduction. So they consist out of 4 phases. So we have 3 mandatory phases, so to speak: create, update, and close. And then there's 1 optional punish phase in case that something goes wrong. Okay, so we have Alice and Bob, and they want to conduct several different transactions between one another. So what they can actually do is they can create the payment channel, and they do this simply by locking some coins up on the blockchain, like in a multi-sig address. Right, so after they have been locked on the blockchain, they create another transaction off-chain that is usually referred to as the state, that basically gives them each the respective balance. But they keep this transaction off-chain. So this is the state S0 in this case. And now the nice thing is what they can do is they can actually create a new state, so S1 for instance, where the balance is redistributed. So in this case, for instance, Bob has paid 5 of his coins to Alice. And they can actually send money back and forth as often as they wish until they are satisfied and they want to close the channel again. So how this works is either party can basically take the latest state, put it on the blockchain, and they will get their respective balance. And you might have noticed that even though they might potentially conduct like arbitrarily many transactions between one another, only 2 of them go actually on-chain. Okay, so maybe some have wondered also what happens if now Bob, for instance, posts an old state. It might give him more money, for instance. So let's assume Bob posts an old state. So how this is addressed in payment channels is that there is a punishment mechanism which gives Alice some time frame to observe this behavior by seeing basically the old state being published to the blockchain. And within this time period, Alice can go ahead and punish Bob. Okay, so maybe let's dive in a bit more into details for Lightning channels, because they are most relevant in this talk, and they're also the most widely used implementation. Lightning channels are based on the paper by Poon and Dreyer of 2016. And how they work is as follows. So again, we have Alice and Bob. They put some money, lock it up in a multisig address by posting the funding transaction. This goes on-chain. And then they create what I previously called the state. They create a commitment transaction, right? So, and in the commitment transaction, you have the 20 coins, and you can spend them in basically 2 ways. So if you look at the left-hand side of the box, you can see that the 20 coins are paid out to Alice and Bob respectively, according to what balance they have. And on the right-hand side, there is the option of punishment, which means that all of the coins, in this case, because this is the commitment of Alice, all of the coins go to Bob. However, Bob can only do this if he knows the secret X1, which was created by Alice. Okay, and similarly, we have a commitment transaction for Bob as well, which is basically the same. It's just mirrored in a sense, and the punishment relies on Y1, which is the secret of Bob. All right, so these transactions are exchanged off-chain, so they're not put on-chain. And because this is a multi-sig address, the funding, basically the commit transactions need to be signed by both Alice and Bob. And yeah, this is kind of so we have either the payout or the punishment. So how does an update work now? Basically, they need to do the following steps. So first, they create new secret values, x2 and y2, right? Then they create a new commitment transaction. So it would be commit 2 for Alice and commit 2 for Bob with some new balance distribution. They then exchange the previous secrets, so x1 and y1. And this is important because only with the knowledge of this secret, they can then go ahead and punish for this old state, right? And we don't actually want them to be able to punish for the newest state, right? Because this is intended behavior to publish the newest state, actually. All right, so this is a bit of a simplified view of the Lightning Network. In reality, it's a bit more complicated. It requires time locks and hash locks. But as a high-level overview, this will be enough for this talk. OK, so what I've shown previously is we had like some payouts. So basically, the application that we put in the channels are payments. So we might want to also do some other cool applications in the channels. So we could actually go ahead and generalize the concept of Lightning to allow also for discrete lock contracts or conditional payments or something like this. So basically, some kind of contract that can be encoded with, let's say, Bitcoin script or whatever the underlying blockchain is. So we could go ahead and instead of having the payout and punish, we could have an arbitrary number of applications in the commit transactions and the corresponding punish for each of them. And you will notice that, as I pointed out, we have a few key points here. So we have a punish per application. That's the first one. And the second one is that we have a state duplication. So basically, we have to store the applications twice because we have the commit transaction for Alice and the commit transaction for Bob. And also, I want to quickly point out that for this channelization of Lightning channels, there is no formal security analysis. OK, so let me now talk a bit about why these things are issues. So why is the punish per applications an issue? And this is an issue because it incurs a significant on-chain communication overhead in case that there is a dispute. So imagine that there is a dispute, someone posts an old state, then if I'm the honest party, I need to punish basically every output, which incurs on-chain cost. So it's not desirable. And the second one is the state duplication, which, it's bad enough by itself because you kind of need to store all the applications twice, but it gets even worse if you have like nested applications. We pointed this out in another paper, the Bitcoin compatible virtual channels. And basically the high-level idea for this is that if you have nested applications, like think of it channels on top of channels, because you never can truly know which commit transaction, the one of Alice or the one of Bob, ends up going on-chain, you need to actually create, for the nested commit transactions, you need to create them on both of the commitments. So you have 4 now. Now, if you go one step further, you would again need to create the commitment for both parties on all of these 4. So you would have 8. And so you have kind of an exponential blow-up. So it's also not really desirable. So let me quickly go over our contribution. So we gave a formal definition of generalized channels in the Universal Composability Framework that has no state duplication and also no punish per application. We gave an efficient construction that is based on adapter signatures. We also, for the first time, formalized adapter signatures. We gave also a construction for ECDSA and Schnorr. And we did a proof of concept implementation and evaluation of generalized channels and a UC security proof. So maybe let's jump in quickly on adapter signatures. So basically, they were first mentioned by Andrew Poelstra in a mailing list, I believe in 2017. And they are defined with respect to another signature scheme. So for instance, ECDSA or Schnorr. And adapter signatures consist of 4 additional procedures. You have pre-sign, pre-verify, adapt, and extract. And on a high level, how it works is as follows. We have again Alice and Bob. Alice has a statement and witness of some hard relation. It could be a D-log relation, for instance, and a message, whereas Bob has a key pair for the signature scheme. So what they do is that Alice sends the statement and the message to Bob, and Bob can use the statement, the message, and his secret key to create the pre-signature. So this is an incomplete signature that is not yet valid, but Bob can still send this to Alice. Alice can verify that this has been constructed correctly, and if it has, what Alice can do is actually Alice can adapt the pre-signature using her witness to yield a correct and complete signature for the message. And with this signature, if, for instance, the message was a transaction, what Alice can actually do is Alice can, for instance, post this transaction on the blockchain, where obviously Bob will see it, and Bob, using this complete signature, the pre-signature and the statement can extract the witness. So and this will be a witness for the statement. And basically the high-level idea on how this works on a technical level is that we hide the witness within the randomness that is used for signing. But maybe to give you an intuition on how we use adapter signatures in generalized channels is we want to have this property that the party who completes the signature and also then posts the transaction necessarily reveals some sort of secret. So this is kind of the main thing that we use it for in this work. All right, so as I said, we gave the first formal definition of adapter signatures. We gave schemes of Schnorr and ECDSA, which we proved in our model. And I encourage you to check out the full paper if you are interested for the details of this. So maybe moving on now to the generalized channels definition itself and the construction. So basically the core idea is that what we want to have that any off-chain, any two-party application that can be executed on the chain, we want to be able to execute this also off the chain, within these generalized channels. And we defined some properties for this. So I'm just quickly gonna go over them. So we have a consensus on creation, consensus on update, which are pretty self-explanatory. Just that the two parties have the same view on creation and update. We have instant finality with punish, which means that at any given time, an honest party can always either get their actual balance that they have stored within the channel, or they will get the full amount via the punishment. And finally, we also have an efficiency property that it's optimistic update means that it doesn't take, it only takes a bounded number of time. All right, so basically now recalling that we had these two things that bothered us a bit in Lightning, which were that we had the punishment per application and the state application. So what we now want actually is we want to decouple the punishment from the applications. And secondly, we also want to use this adapter signatures to remove the state application. All right, so maybe let's start with the first one. So what we do is we take this existing scheme, and instead of basically doing it like this, where we have all the applications and all the punishments already in the commitment transaction, what we actually do is we first kind of take care of the punishment, and then we split the funding into the different applications. So we call this punish and then split. And as you can see here, we still have the two commit transactions, but instead of having all the apps now within this transaction, we just have one output that basically has all the funds, and they can either go to the applications or to the punishment. So basically, we first decide, is this a valid commitment transaction? If not, we punish, and if yes, only then we kind of have a second transaction, which is called the split transaction, and then basically we have the applications. And we can put them there with any considerations of punishment or anything, because we already took care of this before. All right. So we achieved this decoupling, but we still have the state duplication. So how can we remove this? Basically, what we do is we take this thing here, so having two commit transactions, and we transform it to this. And so now why is this challenging? Why was this not done in the first place, actually? So the thing is, why we have the two commit transactions in the Lightning, actually, is we need to identify who posted the commit transaction on chain. Because obviously, we don't want it to be the case that, let's say, a malicious Bob posts an old state and then also punishes Alice, right? So we only want to be able that the other party, the one that's not posting the commit transaction, is the one that can do the punishing. And like with this one here on the left, this is pretty straightforward, right? Because we have two distinct transactions, and we can already encode in the output that for the one of Alice, only Bob can punish, and vice versa. But how can we achieve this in the with only one commit transactions? And I mean, I already spoiled it. We use adapter signatures for this, and basically giving a brief high-level overview on how it works is Alice and Bob both have the key pair. What they do is they create a new commit and split transaction. They create the statement and witness pair. They exchange the statements. They create the pre-signatures on these statements and the commit transactions. They exchange the pre-signatures, and then they exchange this X1 and Y1, which we already had before. This is the X1 and Y1 is the same as before. This is just a secret to identify that it's an old state. And now what we actually have is that if Alice or Bob, punishes the commit transaction successfully, it means that the other party can extract the posting party's witness. And we can use this witness to actually do the punishing. So as you can see here, the punishing now has kind of two ways of being spent. Either Alice can spend it by knowing Bob's secret YI, and the witness that Alice extracted because Bob posted the commitment. And similarly, if Alice posted the commitment, Bob can extract the witness, and if it's an old state, knowing XI can punish Alice. Okay, so it's a bit more complex in reality how it works, because we additionally require time locks, but this is more or less how the construction looks like. So yeah, to sum up, this is actually really the first bidirectional channel protocol that requires only one commitment transaction and does not require punish per application, and only has some minimal assumptions on the underlying blockchain. So we only really need signature verification and time locks, no other scripting requirements necessary. So again, you can check out the full paper for more details. Let me now also quickly go over the performance evaluation. So as I said, we implemented the proof of concept implementation where we deployed the necessary transactions on the testnet, and we measured kind of the overhead for channelized channels and for LC, which stands for Lightning channels. And we measured kind of the off and on-chain communication overhead for the different phases, and I want to just highlight a few of them. So if we have M applications on the channel, this is here on the x-axis. Here the applications are HDLC, which we've heard in the previous talk. So the more applications that live on the channel, the more kind of expensive it is to perform an update. So you can see that in the Lightning, which is the red line, basically that we have a much more steeper curve for the number of bytes that need to be exchanged. And this is because we need to actually take care of this punishment and exchange the corresponding transactions for this. So actually for Lightning, we need to exchange for every update where there are M HTLC, so M applications, we need to exchange 2 plus 2M transactions, whereas in generalized channels, we only need to exchange 2 transactions. I mean, it's still not constant because the 2 transactions have also a linear number of outputs, but it's a much more like flat curve. And the second one I want to point out is during the punishment, and this is really where the benefit of generalized channels comes in. Here it's really just a constant cost, no matter how many applications we have. Whereas in Lightning channels, again the red one, it's again linear. We need to post a linear number of transactions, and for generalized channels it's only 2, and this time not even with a linear number of outputs. So now what applications can we host on generalized channels? As I mentioned, basically we can host any two-party application that can be executed also on the underlying blockchain. Maybe to be a bit more concrete, this would be, for instance, a fair two-party computation or channel splitting or even virtual channels. So maybe to wrap up and come back to this first slide that I've shown you. So we achieved the efficiency and the cheapness because we only have one commit transaction. We are application agnostic because we have this punish and then split, so we don't need to actually worry about how we incorporate the punish within the application. And we're interoperable because we have a very minimal assumption on the underlying blockchain. As I mentioned, only time locks and signatures. So it's really compatible with a lot of blockchains. So maybe just to highlight some follow-up work that we did on this. So there is, for instance, sleepy channels, which is another payment channel idea where we actually don't need the parties to constantly monitor the blockchain to spot misbehavior, and they also don't need to employ watchtowers, so they can actually safely go offline. We have worked on virtual channels, basically what I've highlighted also, where you build channels on top of other channels. And finally, to give you a small teaser for tomorrow, there is also, we also worked on a new payment channel payment scheme. So stay tuned for tomorrow afternoon for that. Thanks.
Thank you, Lucas. Any questions?
So when you talk about only using one commitment, with which scheme do you aggregate all of these, and did you use any recursion?
Sorry, can you say it once more?
For the commitment transaction, you mentioned you only use one. So how did you aggregate it over time, and did you use recursion of any kind?
So, I mean, you only have one commitment transaction per party. So if you perform updates, you of course create a new commitment transaction. So you do have multiple ones, but you don't have it duplicated for both of the parties.
I see. So if I'm trying to punish someone for posting something 2 time steps before,
Yes.
do I use the latest witness or the witness that I need to store from 2 steps ago?
That's a good question. You need to use the 2 steps before. So you actually need to keep track of the previous states, which is, I mean, it's the same in Lightning channels as well. There you also need to keep track of the previous punishment or revocation secrets. Here you also need to keep track of the witness indeed, yeah.
Got it. Thank you.
You mentioned that it's very useful to be able to have nested applications, so an application inside an application and inside an application. Do you have any examples of when you might do that?
So one of the, I think, examples that we initially thought about is virtual channels. And basically, the most like naive, let's say, virtual channel is so where you build a payment channel not by going on-chain, but by actually building it on top of 2 payment channels over 1 intermediary. So, and one natural extension to this would be, so if you now want to go over 2 intermediaries, you take the first virtual channel over 1 intermediary plus the next payment channel, and you combine them into a virtual channel over 2 hops. And this is really where these nested applications come into play. And basically, the number of virtual channels stacked on top of one another is incurs this exponential overhead.
Nice. And I also got the impression from your talk that there was this idea in the community that adaptive signatures were going to be very useful before any construction had been written. What made you place so much hope in them?
I mean, there was actually, so after this Andrew Poelstra mentioned it in the mailing list, there have actually been some other constructions that use them. And actually, I mean, we were thinking about a way of really doing this, like identifying who was the one that posted the commitment, and because this is really the main challenge of this work, right? And it turned out that adapter signatures are just the perfect fit for this. Yeah.
Since Mary asked about adapter signatures, and you thought a lot about them, are they only possible with kind of randomized signatures, or could you build adapter signatures from BLS, for example, which are deterministic?
So you cannot build it from deterministic signatures because you really need to hide this witness within the randomness.
Yeah, so more work to do there maybe.
Indeed, yeah.
Relating to the talk before, would you say that the new construction is more or less susceptible to bribery attacks?
I mean, I think, the talk before was talking about HTLCs, which is applications built on top of payment channels. And I mean, obviously HTLCs would be susceptible both on Lightning channels and on channelized channels. So I think it's pretty much the same, or it's like, yeah, so.
Okay, so no difference.
No, unfortunately not, yes.
Oh, thanks again, Lucas.
Thank you.
Okay. Can we now introduce Mathieu Mathai, who is going to be talking about anonymous atomic locks for scalability and interoperability in payment channel hubs.
All right, thank you very much. This is a joint work with Erkan Tahiri from the Vienna University of Technology and Pedro Moreno Sanchez from India Software. And what I'm going to tell you about today is a way to enforce privacy, interoperability, and scalability in payment channel hubs. So we all know, to go back a little bit to the motivation of the topic of this session, payment channels, that blockchain technologies suffer from an inherent scalability issue. You have to store every transaction on chain, and with that, of course, the blockchain gets larger and larger. And it's even worse when it comes to privacy, because that means basically that each single transaction is inspectable by everyone. And the payment channels promise to be, the holy grail for scalability and privacy, because essentially all of a sudden you don't have to store transactions on chain any longer. Okay, you just need to open a closed channel, and all the other transactions are performed off chain. So at this point, we might think, okay, problem solved, right? But if you think about it, well, it's not like that, because payment channel networks introduce themselves scalability and privacy issues. So first of all, in Lightning, the topology of the network is public, and this is required to essentially route transactions along the network. And of course, the more users you have, the larger the network, and the harder it becomes to store it and process it. And the next point is, it is true that we don't have to store transactions on chain, but we have to open channels. And with whom are we going to open channels? Typically with the people with whom we are transacting more often, okay? Which reveals some information. Also, we need to reveal the initial capacity, which is an indirect way also to revealing basically how much we're going to transfer with these parties. And even worse, there exist, see like recent papers at Usenix, probing attacks where one can just start to probe the network to derive the current capacity of each channel. So payment channel networks are great, in other words, but still they don't completely solve the scalability and the privacy issues in blockchain technologies. A promising solution to tackle this scalability and privacy issues in payment channel networks is given by payment channel hubs. And you can view a payment channel hub essentially like a central party to which every other node connects via channel, okay? So all of a sudden, we don't have to open channels around the world, but we have just to open one channel with the hub. And the hub is responsible to route payments from the sender to the receiver. Of course, for this construction to make any sense, we don't have to have any trust assumption on the hub, right? So the system should work securely even if the hub is compromised or otherwise behave maliciously. And in particular, we have three fundamental properties that we expect from a payment channel hub: unlinkability, atomicity, and interoperability. And let me go quickly into each of these properties, okay? Essentially, unlinkability means that the hub should not be able to understand who is paying whom, okay? And this can be formalized in indistinguishability property, where you have two compatible graphs, and the hub is not capable to distinguish whether, say, Alice is paying Bob or Alice is paying Charlie, with the matching transaction to keep the number of senders and receivers, okay? But if you think about it, the intriguing part of this definition is not the definition itself, which is rather expected, but the problems that you may have in enforcing this definition in a payment channel hub setting. Because Alice has to give money to the hub, right? So Alice has also to tell the hub to whom this money has to be given. So it looks like there is no way, basically, to enforce unlinkability in a payment channel hub setting. We will see how to solve this apparent contradiction later on, okay? So the other obvious property that we wanted to have is that the money should not be lost, okay? So Alice gives the money to the hub, and what we don't want is that the hub runs away with the Alice money, okay? What we want is that the hub really forwards the money. In other words, the two payments from Alice to the hub and from the hub to Bob should happen atomically. Either both succeed or none of them does, okay? And finally, we would like to have, for these payment channel hubs, interoperability. That means this construction should work across different chains, and ideally we could use a payment channel hub like a mixing service, or an exchange service, where basically perhaps Alice gives Bitcoin to the hub and the hub returns Ether to Bob, okay? So this concept of payment channel hubs and coin mixing services has, of course, been explored quite a lot in the literature. There exist a number of proposals, not only academic proposals, but actual protocols implemented in industry. So here you can see a list, and I invite you to have a look at the paper for more details. But the bottom line is, none of these proposals fully achieve the three properties I mentioned before. And the one that gets closer to that is Tumblebit, which is the starting point from our work. And this is the protocol that I'm going to illustrate a little bit more closely now. So Tumblebit is a state-of-the-art coin mixing service that is being introduced by Hallman and others in 2017. And the protocol is composed of two parts. There is the puzzle promise and the puzzle solver protocol. And I think that perhaps the most interesting contribution in this work is to show how to solve this inherent problem. So how to give the money to the hub without breaking privacy. And the way this is done is by swapping the protocol flow. You don't have the sender that gives initially the money to the hub, but it's the hub that gives the money to the receiver, conditioned to the fact that the sender will give later on the money to the hub. So let's see how this is done, okay? So the idea is that we create a puzzle. The puzzle comes with a secret key that is initially known only to the hub. And there is a conditional payment that is sent to Bob, but this payment can be finalized only if Bob knows this key, okay? Which initially it doesn't. But what Bob can do is to re-randomize the puzzle. Now you see the re-randomized version in green. And this constitutes the first part of the protocol, the puzzle promise, in which the re-randomized puzzle is sent to Alice. So at this point, Alice performs a payment to the hub, and in order for the hub to get the payment, the hub has to solve the puzzle. Solving the puzzle means revealing the green key, so the randomized version of the original blue key created by the hub, and this key is revealed to Alice. At this point, Alice will forward the green key to Bob, and Bob can re-randomize back the green key into the blue key and finalize the payment, okay? And with this construction, so the last part is the puzzle solver protocol, we achieve atomicity. I'm not showing you the cryptographic details, I just want to, to focus on the core functionalities and keep the presentation high level. Now, this in fact solves most of the problems we have with payment channel hubs and achieves some degree of interoperability plus privacy and atomicity. But interoperability is limited because the construction in Tumblebit relies on HTLCs, which for instance means it cannot be applied to cryptocurrencies like Monero or Mimblewimble or others that do not support hash-time lock contracts. Also, there is a large communication overhead, which is essentially induced by a cut-and-choose proof technique that is used in the protocol realization. And interestingly enough, this construction is affected by griefing attacks. So what is a griefing attack in this context? It essentially is a setting where the hub is asked to perform multiple puzzle promises by locking basically money, okay? And the hub is not receiving money, so it's just collecting money that gets locked on channels without being compensated. So you can view this as a sort of denial of service attack, and the Tumblebit is susceptible to this type of attack, okay? So this is the motivation for our work. We wanted to try to understand whether it's possible to design a coin mixing service that is efficient and that provides atomicity and linkability and interoperability. And as you might imagine, we answer positively in this work. And I'm going to tell you a little bit quickly how we do it and the intuition behind our construction. So before doing that, let me recap these magic adapter signatures that you have heard in the previous talk and that turn out to be extremely useful in a number of chain protocols, one of which is this one, okay? An adapter signature, like Lucas said before, is basically you can view it as a signature, but it's a kind of weird signature because once you sign a message, initially you are not creating a valid signature. In order to be completed, the party needs to have some secret. And once the signature is completed, the secret is revealed to the other party. So more precisely, let's say that we have a condition that is k times g, where we are working in a group where the discrete log problem is hard. And I'm showing you an instantiation in the context of payment channel hubs, okay? To give you an intuition also how we use it. So we start, the hub has the public-private key, constructs the adapter signature on this condition, and this can be finalized using K. This is the first lock phase. Then we have a second phase, this is the release phase, in which Bob, once he knows the key, can finalize the signature and basically get the money from the hub. And once the signature is finalized, the other party learns the secret or the witness, okay? So with this setup in place, we can try to build a payment channel hub based on adapter signatures, okay? This is a first attempt. It will not really work, but it gives a little bit of intuition on how we want to proceed, okay? So we have a condition on which we wanted to perform payments that is k times g. And we start, so we have the first lock phase in the adapter signature scheme to implement the puzzle promise protocol. And in the end, Bob gets a signature from the hub, sigma g, that basically gives him the money under the assumption that Bob knows k, which he doesn't, okay? So this is the puzzle promise. Then Alice performs another payment to the hub, conditioned to the same secret, okay? So at this point, if the hub wants to get the money from Alice, the hub needs to finalize the adapter signature, so needs to put this key K inside, okay? And once this is done, Alice learns the secret. So Alice has paid the hub, but at this point, Alice can give the secret to Bob, and Bob can finalize the signature and get the money from the hub. So this gives us atomicity, but if you are looking more carefully at this construction, you will notice that we have a problem, right? Because we want to have a linkability, and we clearly don't have a linkability because we have exactly the same condition that is used in the two payments. So for the hub is actually quite trivial to link sender and receiver because they are using the same condition, okay? And in particular, this witness is going to be the same also on the left and on the right. So we needed to fix this problem to get a linkability, which leads us to the second attempt. And I will give you again the intuition for that. So the idea is that we introduce a re-randomization, like in Tumblebit, and the puzzle that is sent from Bob to Alice gets re-randomized in a way that the hub, once solving the puzzle received from Alice, doesn't have a way to really link the secret that is used to finalize the payment from Alice with the secret that is used to finalize the payment with Bob, okay? So recall that in our case, the puzzle is just the condition, k times g, and the solution is k. So essentially what we do to randomize this condition is to get a randomness, and we multiply the condition by that, and we get r times k times g, and then it's indistinguishable from the original condition, and with that we get a linkability. Except that we have a problem at this point, because we can re-randomize the condition, but if we do so, the hub has no way to open at this point the puzzle because he does not know any longer the solution to the puzzle because it has been re-randomized. So in order to solve this problem, the idea is to encrypt, basically, the solution to the puzzle. And for that, we use a linearly homomorphic encryption scheme in a way that basically Bob can re-randomize the ciphertext. Then this ciphertext gets decrypted by the hub can solve the puzzle because by decrypting the ciphertext he sees the solution, but this solution is the re-randomized version of the solution that the hub has constructed with Bob, okay? So this is the key basically to solve the problem that we have of keeping a linkability while at the same time allowing the hub to solve the puzzle. So this is a little bit how we essentially use this data signature with encryption to solve the problem. We encrypt the witness K, and this encryption is sent to Bob. And then what's happening is that we randomize the condition, getting C prime, but at the same time we also essentially randomize the condition inside of the ciphertext by exploiting the linear homomorphic property. And with that now, by decrypting the ciphertext, the hub knows the solution to the puzzle and can just open the puzzle, and the protocol works as you would expect. So this is essentially the full view on the protocol. We start with the puzzle promise. We use our adapter signature. Bob provides a first randomness, and this is then also provided in the second phase by Alice. So we randomize basically the ciphertext and the condition twice. Why twice and not once? Because we want Alice to be protected in terms of linkability, even in case the hub is colluding with the receiver, okay? So for that, we have a double re-randomization. And at this point, as I said, the hub can decrypt the ciphertext, gets to know R times RA times RB times K. At this point, RA can be removed by Alice. Bob learns RB times K, and with that can get K, and the protocol concludes, okay? So we get atomicity, we get unlinkability, and we are also not using any type of HTLC, so we are compatible with cryptocurrencies that don't support them, okay? And what is important, look at the two conditions, they are indistinguishable, okay? So take this as a take-home for a linkability. Now, what I mentioned at the beginning was that Tumblebit suffers from a griefing attack, and let me show you how we can solve that. So the idea is that the protocol at this point doesn't start with the payment from the hub to the receiver. Instead, Alice has to lock initially money for the hub before the hub starts with the puzzle promise protocol. So this is done by essentially performing a payment to the hub, and the hub releases a token. This token has to be re-randomized for privacy reasons and is sent to Bob. And before starting the puzzle promise, Bob has to show to the hub that he has received the token. That means that there is enough money that is locked by some sender, okay? So given the re-randomization, the hub still has no way to understand who is the sender that is providing money for the receiver, but the hub can keep track of the tokens that have been released and will not perform more puzzle promises than those that are enabled by the senders that want to start the protocol, okay? So that's pretty much the idea. All right, we have performed a performance evaluation. A12 incurs 33 times less bandwidth overhead and provides 2 times speed up as compared to Tumblebit. These numbers that you see on this slide are obtained by an implementation where we have deployed 3 Amazon Web Service machine in Oregon, Frankfurt, Singapore, and essentially most of the running time is the network delay, okay? So the time that it's needed to send messages around the globe, okay? So otherwise, the implementation is very efficient. And these numbers, by the way, are instantiated on ECDSA. To conclude, I would like also to give a teaser on a follow-up work that we have in collaboration with our colleagues Glaser and Malavolta from the Max Planck for Security and Privacy, and Tyagarajan from CMU. So in this work, we basically identified a security gap in the original security model for payment channel hubs that we fixed by introducing a more elegant primitive that we call the blind conditional signatures, and for which we have 2 different instantiations. One that satisfies a game-based notion, and another one that satisfies a universal composability definition. These 2 realizations offer different trade-off in terms of efficiency and security, and I invite you to have a look at the paper for further details. So to conclude, A2L is a cryptographic protocol for coin mixing that achieves security, linkability, and interoperability. It comes with game-based as well as UC security proofs. If I would have to say in 3 sentences what are the advantages of A2L, well, first of all, it's backward compatible with most of the cryptocurrencies because it does not require HTLCs. It offers, for the first time, protection against griefing attacks. And as far as I know, it's at the moment the most efficient Bitcoin-compatible payment channel hub realization. You can take a look at the papers for further details. We have an implementation that is publicly released, and if you have any question, I'm glad to answer them. Thanks.
Thank you, Matthew. Any questions?
Hi, great talk. I wonder, so early on you introduced this framework when it relies on a central party. I wonder, and this is a very rigorous analysis so far. I wonder how you think of the possibility of having reliance on not just one central party, but let's say a group of miners, just like in blockchain. So let's say a group of central parties, so that even when some of them are not reliable, this can still work. Would the extension be natural, or would it require more work? I kind of wonder how you think. Thank you.
Okay, so we didn't think about it, so I don't have a result ready for that. in terms of security, okay, the protocol works. I wanted to stress it, even if the hub is compromised. But of course, for the functionality of the system, if the hub goes down, then we're lost. So my intuition will be that using threshold encryptions and in general threshold crypto, we should be able to essentially lift this construction to a multi-hub setting. But of course, this is my intuition. I don't have worked out the details. That will be my understanding.
Thank you very much.
So thank you for the great talk. So in the case for preventing the griefing attack, you mentioned that the sender will issue the sort of the payment, initiate the payment. And the token that the intermediary, the hub, sends to the sender, how can like the sender not do a replay attack, like send it to someone else multiple times, you know, to other people?
So,
because one thing that I wanted to add, because the token, the hub doesn't know who the sender is, right?
That's right. So that's the reason why we randomize it. So in a sense, we are not offering the guarantee that, okay, for this exact, so we offer the guarantee that there has been enough money that has been allocated to the hub, and that the hub is not performing more puzzle promises than those that are enabled by the senders who in this epoch, let's say, have deposited a collateral for the hub. So that's basically the idea behind the token. The token itself does not reveal by whom it has been created or for whom, because of course this would otherwise break unlinkability. But what is important for the hub is to know that it can produce a number of puzzle promises that matches the collateral that has been, let's say, initially allocated by the sender.
Got it. Thank you.
That's the high-level view.
Yeah, thanks.
Is Bob able to identify that this first promise, the griefing thing that you described, is he able to know that that randomized green certificate came from the hub and Alice didn't just make it up?
So like this token is received from the sender. So Bob receives the token from the sender. So he will know that this token has been created by the party with whom it is transacting, but not the hub, due to the re-randomization that is happening in between.
So doesn't that just move griefing from the hub to Alice? Like Alice can now just make a whole bunch of ones and send them to...
Well, Alice has to allocate money first. So while getting the token, Alice has to allocate the money. So it's not a griefing because there is a collateral that is locked.
Thank you.
What kind of metadata would and would not be available to someone doing an empirical analysis on this scheme?
Sorry, can you...
What kind of metadata? So, for example, would you know the payment amounts, even if you don't know who the sender is, and that sort of thing?
Right, so I abstracted away from a number, right? This is a great question. I abstracted away from a number of details. So you might indeed ask, what about the payment amount? So if there is a person that pays 4.678, then isn't this breaking unlinkability? Obviously, the answer is yes. But like in many coin mixing services, for instance, we use the same unit within an epoch. So basically the idea is that you define periods in epochs. Within this epoch, you need to have enough, first of all, users. Empirical data also are related to how many users are participating in the service. If there is just one sender and receiver, the anonymity guarantee is not really great. And also, we enforce that the amount of value that is transacted in each payment is the same. So there is no way to exploit the amount of value that is transacted to the anonymized users.
Okay, thank you. And you mentioned that one of the other things you have to do in order to break linkability is encrypt. So you have an encryption at some point so that you don't have a match between what Bob is sending and what Alice is sending. But you also have it that the channel is able to decrypt so that they're able to solve. By decrypting, are they breaking any anonymity guarantees there, or is this something that doesn't happen?
So basically, the idea is that we essentially, again, we divide the execution of the protocol in certain time periods in a way that also we try at least to reduce factors like timing, for instance, that otherwise would be effective to the anonymized users. But of course, if you want real privacy guarantees, you need to close all the possible side channels. And of course, we can close some, but I'm pretty sure that if you look carefully, there will be some type of practical side channels that emerge. But of course, we by dividing in epochs, we get rid, ideally, on that. Of course, there can be other implementation details, delays in the network, whatever, that could be exploited, but this goes beyond, let's say, our formal model.
So you're using timing epochs to prevent that sort of thing?
Yes.
Yeah. Any more questions? If not, then let's thank our speaker and all the speakers for today. That concludes this morning's session. Thank you, everyone.